Yeah. So today I want to talk about the project I have been working on from after DEF CON. It's called Web2 ID Nullifiers using vOPRF. So basically, what is this project about? So shortly said, it's about vOPRF's usage to enable pseudonymous systems for Web2 IDs. So to remind you, pseudonymous system is a privacy-preserving system where users' actions are linked to unique identifiers. We can call it pseudonyms as well, but not their actual identities. Example of such protocols, such systems are, for example, Semaphore, RLN, Plume, etc. So basically, all of the protocols that has this kind of what we call nullifier is actually pseudonymous system. But there is a problem because there is no way to generate nullifiers for or from public data. And actually, Web2 ID is actually public data. So if we remember the Semaphore, for example, we register. We have this like separate registration phase where we basically generate some random identity key and nullifier for ourselves. We commit to it, and then we reveal this nullifier. We can do similar, but actually we want to use this kind of like protocol. For example, for like in apps where we need pseudonymous systems actually, and where we need these three properties. It's like these properties are anonymity, uniqueness, and eligibility. So basically, if I bring an example, let's say we want to build a voting app where all of the PSE.dev mail holders will be able to vote, for example. The thing is that it's not possible to do it right away. To achieve, basically, it's not possible to achieve these three properties simultaneously. So basically, we can, for example, achieve anonymity and uniqueness. That's actually what we have with Semaphore. But with Semaphore, there is no straightforward way. There is no direct way to prove that we are eligible for voting in this kind of voting. And we can also, for example, achieve anonymity and eligibility. For example, to prove that we are holder of PSE.dev mail, we can just do zk mail proof, and we can output a commitment to our user ID and hash it with some random salt. But nothing prevents us from generating new random salt. That's why it won't be possible to track if we really voted only once. So basically, it's called Great Trilemma problem described by Rarimo team. So basically, what we can do is we can try to get closer to the ideal, but there is no, as I said, it's not possible to achieve three properties simultaneously. Maybe unless we have I/O. So also, I wanted to say, if you have any questions, please free to interrupt and ask. Yes, I'm not reading the chat. So what is vOPRF? vOPRFs are it's also like it's basically verifiable, oblivious pseudorandom functions. Are protocols that allow a client to generate deterministic random based on their input while keeping it private, and at the same time having a verifiable output by providing cryptographic proof. So basically, we have an output from this OPRF. We have a random number, and we can say that, and we can verify that it was really indeed generated by this party, and with these inputs. It can be created using MPC. So the simplest using, for example, app-specific MPC, and that's what we're going to have in this protocol. It can also be constructed with cosnarks, for example. So the idea is it's possible to use a vOPRF to generate nullifiers based on the public input, because, as I said, we can keep it private. So it's basically possible to put, for example, Web2 ID and send it to vOPRF, and it will generate this random number based on that for us, and it can serve as a nullifier. This is just like a high-level idea. So now I want to explain how it works generally. Does anyone have questions for now? Okay, I can continue then. So I said that I put here that we have two parties generally. So first one is user with Web2 ID, for which it's possible to create zk-mail proofs. And also in this presentation, I talk about zk-mail. I put zk-mail in the protocol as an example, but generally we can also use it with any other protocols as well, with TLS notary, like zk-TLS generally, with open passport, and etc. And OPRF. And we're gonna use MPC for OPRF. For simplicity, for now, I will just describe it as a like whole party. But later I will describe how we can bring and add multiple nodes here as well. And it will have its own elliptic curve key pair. We use, for example, baby jab curve for snark friendliness. And of course, public key have to be stored in some public registry. So it's like a commitment. So we'll have this key pair, for example, S and S multiplied by H, some random generator. So S is a private key, and this is a public key. So how it works. I described two steps here. Basically, what we could do, we actually could have these two steps. We could put these two steps into one step, but that actually would require for us to change a lot of the code in the zk-mail circuit. But if we separate it into two steps, we can just, for example, output the commitment. So basically, we can just add additional constraint to the zk-mail circuit, and we won't change the code generally. So basically, we will just need to, for example, output a commitment from zk-mail circuit. Basically, we just mix it with some random salt, and I called it commitment 1 here. Generally, I call it auth proof. So basically, it's a zk-mail proof with commitment to user ID. So yeah, user provides this, generates this auth proof, and then also there is a new circuit which actually contains the logic needed for the protocol. And in this new circuit, we do this commitment consistency check. That's the first constraint. We basically check that we basically put this commitment as a public input, and we check that yeah, we indeed know the user ID and salt. And next step, what we are doing here is that we are calculating hash to curve from our user ID. I called it G. And now, generally, we would need to send this hash to curve, this point G, to OPRF. But the thing is, if we send it in a plain text, it will be possible, generally possible, to revert this because user ID, like the set of all user IDs, is not that big actually. For example, if we, for example, calculate if we have user ID, and user ID here is just all of the mails of like PSE.dev, for example, and I don't think it's a big number, we can just calculate hash to curve from all of them, and we'll be able to reconstruct to get that G. So it's basically possible to do a dictionary attack. That's why we need to add some blinding factor to that as well. And for that, we will just generate random number R and multiply G by it. I called it commitment 2. So basically, commitment 2 is an elliptic curve point as well. Anyone has any questions? Okay, I'll continue. So now we send this auth proof, and this stuff, basically commitment 1, commitment 2, especially to the OPRF. And OPRF replies with OPRF response. OPRF response is basically S, and S, as you remember, is a private key of the OPRF node. and we multiply it by commitment 2. And it's basically S multiplied by R multiplied by G. And for verifiability property, OPRF node also needs to attach a discrete logarithm equality proof, as also I can call it, we can call it Schumpeterson proof for such multiplication. Basically, we check the equality of this, basically, of these pairs. Yeah, and yeah, for the last step, user gets this response, and on the last step, user basically verifies all the previous steps, including discrete logarithm equality proof that came from OPRF node, and it also outputs the nullifier. And nullifier is basically OPRF response divided by R. And yeah, we can do division here because division is basically multiplication by an inverse, and that's actually gives us this S multiplied by G, or S multiplied by hash to curve from user ID. So by doing that, we didn't learn anything about this S, and also OPRF node didn't learn anything about our plain hash to curve from user ID. Yeah, so we also can update the protocol by using domain separator app ID to have different nullifiers across different apps. Because right now, if we just go through this process, for example, we have our Web2 ID, for example, our Gmail, we generate nullifier for ourselves. But then if we're going to reuse this Web2 ID across different apps, we're going to have the same nullifier. So it will be easier to track our actions. And we can just add domain separator, app ID, hash it, and we're going to have different nullifiers across different apps. That's also useful here. Any questions for now?
Alex has a question.
Okay. Alex, can you just...
Oh, yeah, I can. So how do we trust the user to divide exactly by R? Is there a proof?
Yeah, so basically this discrete logarithm equality proof verification contains R, if you remember, because we have this commitment 2. And if user will input different R, discrete logarithm equality, basically Schumpeterson proof verification will not work, basically. So we also, as I said, on the last step, we verify all of the previous steps, all of the consistency in the protocol. So we basically recalculate all of the stuff that we had before, and we also recalculate the commitment 2 as well.
Hold on. I think it is because the user want to obtain the nullifier, which is S times the hash to curve of the user ID. So if the user doesn't divide exactly R, it will get like S prime times hash to the curve user ID, and the S prime is the key of another OPRF provider, which is not the one that maybe some system will accept.
No, I think the Alex questions was more about, can we generate, is the system sound generally? Can we generate different nullifiers by just generating new R every time? But generally no, because even if we let's say generate a R value on this second step, and then let's say we use different R on the fourth step, the verification of this Schumpeterson proof will not work simply. But if we, for example, go through this OPRF process again, and on the second step we generate new R, and new R, that actually doesn't that actually won't affect the result, because the result doesn't contain the R at all. All it contains is basically S multiplied by hash to curve from user ID. Does it answer the question?
So what is your question, Alex?
Yeah, I think that the Schumpeterson proof answers my question.
I see. Okay.
Yeah. So basically, yeah, as I said, we have this commitment 2 and we basically check again. We try to recalculate all of the stuff on this fourth step. We recalculate this commitment to again. So basically, if we have different commitment to, it won't be possible to verify this. Yeah.
But do I get it right that only the user should know the random R?
Yes. Yes. I'm not sure that if, yeah, I think yeah, it's a private input. It's a private input. So yeah, but you can notice here, if we have only one node, that will be the result, right? So S multiplied by hash to curve of user ID. Basically, if you have only one node, OPRF node, let's say it has access to this nullifier because it's public, it can basically multiply this value. It can basically multiply the nullifier by inverse of S, and it will just get hash to curve of user ID. And it will be possible to create to do a dictionary attack as well. So that's why we need to add more nodes. So basically, how can we do that? We have actually few options for that. I think there are even more options, but I listed a few. So first two probably simplest. So first one is just we can have n of n NPC. So how to do that is basically we, instead of having only one node, we'll have multiple nodes, and basically every node replies to a user individually. And so user will do this whole process with each node, basically. Let's say if you have 3 nodes, it will do it with 3 nodes. And in the final ZK proof, user verifies all of the individual Schumpeterson proofs, and then it calculates the linear combinations of all the responses, and yeah, of all the responses. And basically, similar, like we can have M of n NPC as well. It will be similar to n of n, but it only requires m responses. So instead of verifying n responses, we can only just verify m responses and calculate linear combinations of m responses. Like other option, as Nam suggested here actually, is that we can have m of n scheme similar to 2 as well, but actually it's a bit interactive. So nodes will just coordinate between themselves, and they can calculate one common OPRF response and one common Schumpeterson proof. So this is actually more laconic even, because we can just verify only like one Schumpeterson proof, and we will have only one OPRF response in the circuit, in the final circuit. But actually for now we stick to second option because it's easier to implement basically. And we can also do the same with BLS, but that actually would add some requirements to the pairing verification in the circuit, and so we're not doing that as well. So yeah, basically by adding MPC, this final result will depend so multiple nodes basically will affect this result, and not only one node. So it will be possible for nodes to reconstruct to get your hash to curve from your user ID with only in case of collusion, basically. Yeah, but yeah. Any questions to that point?
Can you go back to 2 slides before this slide? The first one, yeah. So basically here, even if the user next time create another commitment one with another song, the final result, the nullifier will still be not containing this salt, right?
Yeah. Nullifier only depends on your on your user ID basically.
So you cannot create a new nullifier with a new salt at all.
Yeah, no, they can't. Yep, I think I can go further, right? So yeah, now we have this, like the protocol, I described it already. It's like not that like actually like difficult to understand, I think. It's already useful. And we are actually like working on the implementation of it right now. What we can do, what else we can do on that? What else we can build like useful with this is that we can create one global registry. Like I also call it global semaphore for Web2 IDs. Basically, what we can do is that we'll have one global registry app, and we'll set app ID equals to 0, and it will contain a Merkle tree. So generally, it will be a smart contract. So basically, in this Merkle tree, we'll put, yeah, maybe. So we have this pseudonym. I will just rename, like before I called it a nullifier here. But we can say, for better understanding, basically, we can say that we can call it pseudonym, and it will be hash of this OPRF response, like SG and 0, because we set app ID to 0. And we'll store pub key that's equals to hash of pseudonym and commitment 1 in leaves. So if you remember, commitment 1 here is a hash of user ID and salt. So basically, user has to save the salt from the first step. And we'll store pub key in leaves. So basically, by doing that, we'll eliminate the need basically from for going through this whole process again and again. For example, let's say we have a Web2 ID, our, let's say, like Gmail account, and we want to use it anonymously with nullifiers across different apps, let's say like in some voting, in airdrop, in, I don't know, PSE forum, like etc. If we don't have this anonymous registry, that would require us to go through this like OPRF process again and again. But in this case, with global registry, we can only add our identity only once. We can put it in Merkle tree, and then we can reuse it. So basically, what we're going to have is we're going to have this global Merkle tree root with all these like leaves with pub keys stored there. And we also, let's say we have some additional app, some app that is using this, and this app has its own app root as well. So basically, to do an action, we'll provide ZK proof of membership in an app's Merkle tree, as well as in the global Merkle tree, and verifying consistency across two. So we'll calculate nullifier by just, as I described before, so nothing new here. But that actually, as I said, will eliminate the need from going through this whole process again and again. So with checking just like two membership proofs and verifying consistency, there we won't need to even generate new ZKML proof, for example. We won't need to go through OPRF MPC. We'll just have nullifiers. Yeah, and we can say that here in this protocol, the pair SG and salt will be an action key, and SG itself will be like a viewing key, because anyone who will have this pair SG and salt will be able to generate proofs in this system and do an actions for us. And SG is just like a viewing key. So anyone who will have SG will be able to track our actions across different apps. Not revealing like who exactly we are, but just revealing our like identity generally, like revealing our like pseudonym across different systems. Yeah. Anyone has the questions about this? Should I go forward?
Yeah, actually, if the nullifier is only the hash of SG and app ID, then you can only use the nullifier once, right?
That depends on the app generally, because if the app doesn't prevent from using
No, what I mean is that people can just link the usage of you in the same app using this nullifier.
uh, I don't fully understand the question. Sorry. You mean like if we used the app once with our like,
So you use this by revealing the nullifier, right? And do something.
yeah. So yeah, we
Yeah,
basically do this like two proofs, as I said. Like it will be generally like one proof. And the
right. But
output will,
then it means that let's say that for the first time you use the nullifier, that is like the action key to do something. And then again, you use the same nullifier to do something. Then people can link that to actions if you are in the same application.
if you are in the same application, yes.
Yeah, then maybe we can like include something like session ID or
Yeah.
something.
Yeah, that actually like was the suggestion. We had this. I decided not to include like too many information into this presentation because like I already like put too much in. Yeah, but
Okay.
generally
Yeah.
yes, that like was a suggestion from some I don't remember his name, from Polygon ID, I think, team, from
Okay.
Private ID team. They also suggested similar thing, that we can add session ID here as well, like an epoch kind of. Yeah. So generally yes, and this is actually was like my personal idea and also Lev's idea, but actually I found out that Rarimo team is actually working on something similar, not specifically with all of this stuff with nullifiers for Web2 identities with vOPRF, but generally they also in EIP 7812 they are building this global registry where people can just put like different information. So for example, if we will develop this, we can actually go, for example, with their specification and yeah, just reuse their stuff. Yeah.
Is the reason why you have salt in for an action key but not for the viewing key is also because you don't want to connect two different actions in the same app or something?
No, I just said that this is an action key because having SG and having salt, you will be able to do an actions for this like specific user basically.
So salt is the hash of the user ID. Yes, sorry. Salt is used together with the user ID in commitment one. So
Yeah,
you
it's
want to
kind of
hide,
like secret.
you want to avoid dictionary attack on user ID. So you have to add salt.
Yeah.
I see.
Yeah. Yeah, it's actually like a secret. It's a private input. Yeah. Anyone has more questions? Okay, I think I can also describe Rarimo's approach to like similar stuff. So basically, Rarimo is a company that they build different things, but one of the like famous thing they built is a freedom tool, freedom app. It's a voting app for passports. So we have the similar problem with passports as well, because passport data, we can verify them. We can verify the biometric. We can verify the public key, we can verify the signature provided by chip in the passport. But we have the same problem. It's not possible to generate nullifiers for this data. For example, if you have a voting, it won't be possible to generate nullifiers right away. So their approach is that generally it's similar to semaphore with a separate registration phase. So the users will hold a key pair, just like basic, like I don't know, if like Ethereum, for example, key pair. and they'll add themselves into a global Merkle tree, like this EIP 7812, as I described before, by providing an auth proof as well. And auth proof is actually similar to what I called auth proof as well, like the one that was on this first step here. Auth proof is, in their case, auth proof is basically passport verification. And also they commit to public data. In their case, it's basically a hash of passport data group. And this actually, like this approach is trustless because it doesn't rely on any other party or MPC as well. But generally, it lacks privacy because it's possible to do a dictionary attack and de-anonymize. So they don't add like any random salt here. So it's basically like committing to a hash of passport data. What they rely on is a network privacy effect. So basically, the more users registered in the system, the harder it will be to track who exactly performed the action. So it's similar to Tornado Cache. Yeah, so their solution, I discussed it with them. They said, I asked why, like I told them that it's not anonymous. They said that they're not aiming for now for large scale deployments generally, and they don't do, for example, they don't host like that important kind of like national votings. And what they wanted to eliminate, what they didn't want to have is basically like another party. They wanted just a trustless, like self-issuance mechanism for nullifiers. But actually, like I had an idea, and we also can think about this more, is that we generally can combine like our approach and Rarimo's approach for global registry. So basically, we'll do like the same stuff as Rarimo in their Freedom tool, but instead of committing to a public data, like instead of just publishing hash of passport data, we can publish like vOPRF response to this hash of passport data. So basically, by doing that, we're gonna have like kind of like the best from two protocols. We're still gonna have like MPC security, and in case of collusion, in case of vOPRF is broken, we'll have privacy network effect that Rarimo team relies on. Yeah, that's actually it. Anyone have a question on that? Yep. Okay. And I also wanted to list a few open questions we have. I think generally we have more open questions, but the few I remembered is like first thing is probably vOPRF network spam prevention. So basically, should it charge money for its services? Because if there is no spam prevention mechanism for vOPRF network, it will be just possible to attack it with spam, to provide some to do some kind of attack, to provide like multiple like auth proofs and just DDoS the system. So there should be some mechanism for spam prevention. Maybe it's a good to just add a fee or something, or just burn Ethereum, for example, when we use, like every time we use vOPRF. Like another question is MPC threshold parameters. Is generally how secure we want our MPC, and that actually depends on. Next question is, should we like generally target large scale deployments? For example, big national votings, so big, like some kind of like very important apps where the where the de-anonymization of users might be critical, might be like really bad, or we are just good with going like for some small scale deployments, for example, for kind of like organizational small votings, like airdrops. So basically, where the attack price will be more than like the result incentives, basically the profits incentives, and yeah, more use cases and applications. If you have ideas for this protocol, basically, feel free to like. I'll be eager to discuss. Yeah, that's it. Thank you.
Thank you, Rasul.
Anyone has a question?
We also have a Discord. I mean, you know it probably. We have this OPRF Discord channel in the research section, and we have on Wednesday, 11 a.m. CET, a weekly meeting. If anyone is interested in that, can join.
Yeah. Okay. If nobody has a questions, I think we are good to finish this, right?
Yep.
Cool.
Thank you.
Yeah, thank you a lot for coming, guys. Yeah.
Bye-bye.
Thank you. Bye.
Thanks,
Thank
Rasul.
you,
Bye.
Rasul. Bye.
Bye-bye.